This is a recording of the final project for Duke University course Machine Learning Foundations for Product Managers. Here, the objective of this project is to build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery system generators to generate power. We have a bunch of feature variables, so temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output. So the net hourly electrical energy output is the target variable that we're trying to predict. First, we import a bunch of libraries, pandas, numpy, matplotlib, etc. And then we read the data from CSV. We look at what the first few rows and columns of the data looks like, looking at the count, the mean, the standard deviation. So basically looking at the summary of the data, summary statistics of the data. So AT, V, AP, RH are our feature variables, and this is the target variable. It's also generally a good idea to look at the first 4 or 5 rows of the data to see if there's not any surprises. It's a good idea to look at the tail of the data as well to see that here we can see we have 9,567 rows. Now let's examine whether the target we're trying to predict is has a normal distribution or not. And if it has a normal distribution, then linear regression would probably be the way for us to go. We can see here that it actually has 2 different peaks. We're looking at the Johnson SU normal and log normal distributions. Let's look at the shape of the data. So the data set has a total of 9,568 rows and 5 different columns, so 5 variables. Let's try to see if there's any missing values. Looking at the percentage of missing values, you can't see any missing values. So the data set is fairly clean, which is really good. Now we find the correlation coefficient between our predictive features and target variables. So looking at this table right here, we can see that there is a negative correlation of ambient temperature with the feature with the target value we want to predict. There's also a negative correlation of the pressure. I think this is the pressure we want to, there's a negative correlation between these 2 variables. From the above, we see that negative correlation between, I just mentioned electrical energy output and ambient temperature, as well as exhaust vacuum. So that's not pressure, that's exhaust vacuum. Let's create a correlation matrix heat map to get more clarity. So going through the heat map, you can see that these 2 features are very correlated. So a correlation of 0.84 of ambient temperature and whatever this variable was, exhaust vacuum V, and then also a negative correlation. So slightly lower correlation here between RH and PE, and also significant negative correlation between the target variable and ambient temperature, and then also the same exhaust vacuum negative correlation here as well. There's very mild positive correlation here, but it's 0.5, so it's not very high. It's a good idea now to look at a scatter plot to see the correlation of these variables. From the above, we can see that both AT and V, so ambient temperature and vacuum, have a linear negative relationship with PE, as I already mentioned. Also see that AT is more negatively correlated with PE than V. So therefore we'll likely drop V and choose AT for our model. So I think later I've included all of our variables, but for us to begin with, I think AT will be the starting point. as our single feature we want to use to predict the energy output. We'll build a few different models to evaluate and evaluate which one works best. We will be building 4 different models because there are only a few variables that we are going to use. We need to use, or we can use, to predict. Initially, we'll start off with just using ambient temperature to predict energy output. Then we'll use ambient temperature and AP, and AP stands for ambient pressure, to predict the energy output. And then we'll use ambient pressure, RH, and temperature to predict. And then finally, we'll also include the vacuum, which was negatively correlated, but also highly correlated with AT. So it was kind of a twin brother of AT. So this is what we'll do, and we'll choose 3 types of algorithms. We'll choose linear regression, decision tree, and random forest, and evaluate them all to see which one of these will perform the best. So we're trying to define some data frames here. I will extract from the existing data set. I will extract just the data for ambient temperature and call that data frame 1. I'll extract ambient temperature and ambient pressure and call that data frame 2, and so on. And then I'll put Y, I'll define as another data frame Y as the target variable PE. So that's the energy output. Net electrical energy output. Okay, so we are now ready to import some libraries. So we will use scikit-learn to import a bunch of train tests split. We will import this. We'll import linear regression, decision tree regressor, and random forest regressor. Here, we're splitting our data into training set and test set, so 80% training and 20% test set, as was mentioned in the lecture. And then test size of 0.2. Okay, so that's saying 20% of test is the test set, and then random state is 0. And we're going to do that for linear regression, for decision tree regression, and for random forest. And then we also imported the metrics for evaluation earlier. This was done right here. So we imported mean squared error, R-squared score, and the mean absolute error. We're going to use these 3 metrics to evaluate model performance. And then model evaluation, so we use these 3 metrics, and I'm just trying to set them up here, setting up a list of evaluation metric scores using this code right here, and then printing the scores for all of the models. So I've used a list function to print the scores, and as you can see, models for DF1, so data frame 1 is only using 1 variable, the ambient temperature, and I've got linear regressor, decision tree regressor, and random forest regressor, and I have the values here. So list of evaluation metrics. So this spun out a bunch of evaluation metrics. I think this is the mean squared error, this is the absolute error, and this is the R squared. But just so I can read it properly, I've rejigged this a bit and printed it in nicer format. So this is using a single feature. This is from data frame 1. So looking at the linear regression, the root mean square error is 5.2. Mean absolute error is 4.1, R-squared is 0.9. Looking at decision tree, 5.9, MA is 4.6, this is 0.8, so it looks like decision tree for a single feature performed worse than linear regression, and then random forest also is seeming to perform worse. This for a single predictor, this seems to be doing well. For linear regression, seems to be doing well. For two features, let's see, 5.2, 6.7, 5.0, 0.91. So this is doing slightly better in terms of R-squared. This is doing actually quite well in terms of mean absolute error. And then this is not so good. So for two different features, we have a winner, random forest. What if we use three features to predict the variable, to predict energy output? We are looking at an overall reduction in terms of errors, root square error, and mean absolute error compared to two features. So three features overall looks to be doing well. Linear regression is 4.6, 4.2, so random forest wins. Mean absolute error 3.7, 3.2, again random forest wins, and R-squared is 93% and this is 92%. Okay, so if we use three different features, then clearly random forest is winning. What about we use all the different features? And I'm a bit worried about this because the vacuum and ambient temperature were highly correlated, but let's see if that makes any difference. So 4.4, 3.5, 4.8, 3.1, and this is 92%, this is 93%. That's a tough one because the absolute error here is slightly smaller, the absolute error here is slightly larger, and then root mean square error here is slightly smaller, root mean square error here is slightly larger. Okay, so this, I'll come back to this. And then looking at the random forest, there's 3.2, so I didn't actually have to make a decision between these two because this one is clearly the winner here. And then mean absolute error is 2.3, again clearly the winner. And then R-squared is 96%. I think this is probably the highest R-squared that we've observed. Okay, so that's 93%, that's 91%, that's 89%. Okay, so looking at all of the different sets of models, it seems like we have a clear winner in random forest. So we will be choosing random forest as our go-to model for predicting the outcome variable, which is electrical energy output. Thank you.